Hello, my name is Thomas Nelson, and I'm here to tell you about our paper, Computer Vision for International Border Legibility. This is joint work with Trevor Ortega, Skyler Crane, Josh Myers-Dean, and Scott Wehrwein. In this work, we propose a novel vision task we call border legibility estimation, collect a dataset, and establish several baseline techniques for this task. Why are we studying border legibility? We're collaborating with some political scientists who are interested in how international policy shows up on the ground, especially in terms of visible displays of control along borders. In political science, this has applications in understanding geographic and policy features, like land use, property rights, immigration policies, and border security. Prior work in this area relies on labor-intensive human annotations, limiting the scale of the analysis. Our goal is to provide automated methods that further our understanding of how borders appear all over the world. To turn this into a computer vision problem, we propose to estimate what we call border legibility, the extent to which a border can be visually detected in overhead imagery. In these few example tiles, the less legible borders appear on the left and the more legible ones are to the right. The most obvious features that give rise to legibility are low level, where there is an obvious color contrast, for example, due to a road or river. However, some borders are legible because of higher level features. For example, sometimes there is a clear change in land use or border security infrastructure. We think this makes for an interesting vision task since the relevant features range from low to high level. We started by collecting a dataset of overhead image tiles at international borders. Using GIS data in the Bing Maps API, we collected over 600,000 tiles with dense coverage of all of the international land borders in the world. For evaluation, we collected a small validation dataset of relative legibility judgments. We asked workers on Amazon Mechanical Turk to tell us which of two tiles had the more legible border. Our validation set contains 12,000 comparisons among 1,000 randomly chosen tiles. Because the comparisons are pairwise, we found that it would be too expensive to collect enough ground truth annotations for supervised deep learning methods. Instead, we propose a couple different feature comparison baselines and one deep network trained with a self-supervised approach. For all of our methods, we consider each tile to be segmented into three regions. A and C are the regions on each side of the border, and B is a margin around the border. Our feature-based methods compare collections of image features extracted from each of these regions. The most successful of these methods works by comparing the distribution of cluster assignments. We first use k-means to cluster the image features in the whole tile into three clusters. Then, we calculate the distribution of cluster assignments over the entire image. Comparing this to the distribution of cluster assignments in each of the regions, A, B, and C, gives us a measure of how distinctive the regions are. The largest of these distances is our predicted legibility score. As input features, we tried out RGB pixels and CNN features from a few different layers of a pre-trained ResNext model. Our self-supervised Siamese network, which we call border cut, takes two tiles and predicts which is more legible. To train it, we use an augmentation scheme inspired by CutMix. We create artificially legible tiles by swapping in content from a random other tile into one or two of the image regions. In our results, border cut agreed with human annotators more than any other method. However, our simpler clustering approach does better on metrics that compare rankings of the tiles. We think that there's a lot of room for improvement with more ground truth data and better techniques. Thank you for watching our presentation. Please check out our paper for more details and check out our project webpage for code and supplemental materials.